The letter sits on a card in your wallet. Type O positive. You have carried this letter for decades. You know what it means for transfusions, universal donor. You know the hospital wants your blood because it can go into almost anyone. You have never been told what the letter physically means on the surface of each cell. You have donated blood and watched it flow into a bag labeled with that letter, without knowing what the label physically represents at the molecular level. The letter is not a classification the way shoe size is a classification. The letter is a description of a molecular surface condition on every red blood cell in the body, a condition determined by one gene that carries one mutation that broke one enzyme that left the surface bare. Every red blood cell in your body is bare. 25 trillion cells circulating through the bloodstream right now, each one missing a molecular structure that every other blood type carries. The surface where type A has one sugar chain and type B has another, your cells have nothing. A blank space. The enzyme that would have built the sugar chain carries a deletion in its gene, a single nucleotide missing from the DNA sequence, producing a protein that misfolds and cannot function. The badge-making machine is broken. The badges were never made. The surface of every cell you own is bare where everyone else carries molecular identity tags. Bare surface is the universal donor advantage. The marrow produces 2 million new red blood cells every second, and everyone carries the bare H antigen because everyone is built from one gene with one deletion on one chromosome. It is also a deletion that has been shaping your disease risk, your clotting tendency, your gastric vulnerability, and your evolutionary history since before the first civilization arose. The letter on the card is a molecular surface condition determined by one missing nucleotide on one gene on one chromosome. The physics of what that bare surface does to the body that carries it is what the letter never explained. What is the surface and what is missing from it? Chromosome 9. The ABO gene. The gene codes for a glycosyltransferase, an enzyme that attaches sugar molecules to a structure called the H antigen, sitting on the red blood cell membrane. The H antigen is a sugar protein complex embedded in the lipid bilayer of every red blood cell in every blood type. It is the foundation structure. Type A adds one sugar to it, type B adds a different sugar. Type O leaves it alone, because the enzyme that would add the sugar is broken. The H antigen is the blank badge. The A and B sugars are the identity marks stamped onto the badge. Your cells carry 25 trillion blank badges. The blank badge is not damage. The blank badge is the original design. The stamps were a later innovation. In type A, the enzyme attaches N-acetylgalactosamine, a specific sugar, to the H antigen. In type B, a variant of the enzyme attaches D-galactose instead. In type AB, both enzyme variants are active and both sugars are attached. In type O, the gene carries a single nucleotide deletion near position 261 in the coding sequence. One deleted nucleotide. The deletion shifts the reading frame. Every codon downstream of position 261 is misread. The amino acid sequence after the deletion bears no resemblance to the functional protein. The protein folds into a three-dimensional structure that cannot bind its substrate, the H antigen, and cannot catalyze the sugar transfer reaction. The enzyme is manufactured by the cell, transported to the Golgi apparatus where the sugar attachment normally occurs, and sits there unable to perform its single function. The machinery exists. The instruction set is corrupted. The product is permanently defective. Every cell the body produces from this gene will carry the defective enzyme and an identical bare surface for the owner's entire life. The deletion is inherited, passed from parent to child through chromosome 9 in every generation, one broken enzyme producing the same bare surface across every descendant who inherits two copies of the O allele. The enzyme is produced but misfolds into a shape that cannot catalyze the sugar attachment reaction. The H antigen sits on the cell surface unmodified. No N-acetylgalactosamine, no D-galactose. The bare H antigen is what remains when the construction machinery fails. ABO gene and the single nucleotide deletion producing the type O phenotype is established molecular genetics. Yamamoto and colleagues identified this deletion in Nature, confirming that the frameshift at nucleotide 261 produces a non-functional glycosyltransferase in type O individuals. 25 trillion red blood cells, everyone carrying the H antigen with no A or B modification. The surface of each cell is a molecular landscape where a structure should exist and does not, a blank space repeated 25 trillion times across every red blood cell in the circulation. The teeth discussion described surface chemistry determining structural properties through hydroxyapatite crystal composition. This surface chemistry determines immunological properties to sugar-protein composition. Different surface. Same principle, what sits on the surface determines what the structure can do. The surface is bare. The enzyme is broken. The question is whether a bare surface matters beyond the transfusion advantage you were already told about. Why can bare cells enter almost any recipient? Immune recognition is a shape-matching problem. When foreign red blood cells enter the bloodstream through transfusion, the recipient's immune system scans the surface antigens to preformed antibodies circulating in the plasma. Anti-A and anti-B antibodies form in the first year of life, stimulated by bacterial surface sugars resembling the A and B antigens. By adulthood, these antibodies circulate at concentrations high enough to mount an immediate response to foreign cells. Type A recipients carry anti-B antibodies. Type B recipients carry anti-A antibodies. Type O recipients carry both anti-A and anti-B. When A cells enter a type B recipient, the anti-A antibodies bind the N-acetylgalactosamine sugar on the A cell surface. The antibody paratope fits the antigen epitope the way a key fits a lock, a three-dimensional shape recognition at the molecular level. The antibody distinguishes N-acetylgalactosamine on A cells from D-galactose on B cells despite both being similar sugars, because the three-dimensional contours of their hydroxyl group positions differ enough for the binding site to tell them apart. The binding triggers the complement cascade, a series of proteins that assemble on the cell surface, punch pores through the membrane, and lyse the cell. The red blood cell ruptures. The hemoglobin spills into the plasma. Agglutination, the clumping of antibody-bridged cells into masses that block small vessels, occurs simultaneously. The transfusion reaction can be fatal within minutes. The lethality is proportional to the volume of mismatched blood. A small mismatch triggers a limited complement response the body can contain. A full unit of mismatched blood triggers a systemic complement activation that can produce renal failure, disseminated intravascular coagulation, and cardiovascular collapse. The severity is why blood typing exists, why the cross-match exists, and why every unit of blood is tested before transfusion. The molecular surface chemistry on the red blood cell membrane is the variable that determines whether the transfusion saves or kills. Type O cells enter the same recipient. The antibodies scan the surface. Each antibody is a Y-shaped protein with two identical binding sites at the tips of the Y, each site shaped to recognize one specific three-dimensional molecular structure. Anti-A antibodies carry binding sites shaped to fit the N-acetylgalactosamine sugar. Anti-B antibodies carry binding sites shaped to fit the D-galactose sugar. The binding is exquisitely specific. A difference of one sugar, one molecular shape, one three-dimensional contour determines whether the antibody binds or passes. The antibodies find the H antigen but no A sugar, no B sugar. The paratope searches for the three-dimensional shape it was built to recognize. The shape is absent, no binding, no complement activation, no agglutination, no agglutination, no lysis. The cells survive. Universal donor status works because the deletion removed the molecular targets the immune system scans for. The removal is complete and permanent. No type O cell, anywhere in the circulation, carries any A or B antigen. The absence is absolute. The safety margin the absence creates is why type O negative blood is the emergency default when there is no time to target the recipient. The bare surface is immunologically invisible to anti-A and anti-B antibodies. The advantage you carry is the absence of something attackable. Well, the shape-matching physics reframed the universal donor label I had been interpreting as a simple category. The label is not a classification. The label is a molecular surface condition on every cell in the circulation, each one carrying a blank space where every other blood type carries a three-dimensional structure the immune system can recognize and destroy. The universality is deletion. The safety is absence. Bare cells enter almost any recipient because there is nothing to attack. The Western assumption for a century was that this bare surface was a later mutation, that the functional enzyme came first and the deletion came second, that type O was a degraded version of A. The genetic evidence reversed this entirely. Which blood type came first? Type O is the oldest blood type. The ancestral human population carried the bare H antigen. The functional glycosyltransferase, the enzyme that builds the A and B sugars, evolved later as a gain of functioning. Types A and B are built versions of O. The sugar additions came second. The bare surface came first. European assumption that type A was original, because A is common in European populations, ran in the scientific literature for decades before genetic evidence reversed it. The direction was backward. The correction required genetic evidence from multiple populations, phylogenetic analysis of ABO allele diversity across primate species, and molecular clock estimates of mutation timing. The ancestral allele is O. The A and B alleles arose through point mutations that restored enzyme function, adding sugar-building capability to a gene that originally lacked it. The evolutionary narrative reversed. The functional enzyme is the innovation. The broken enzyme is the original. Type O was not a deletion from a functional ancestor. Type O is the functional ancestor. The enzyme that builds A and B antigens is the later addition. The bare surface is the original condition the human immune system evolved under. Now, the selective advantage that maintained type O at 37% of the global population for tens of thousands of years traces to the deadliest parasite in human history, Plasmodium falciparum. The malaria parasite. When Plasmodium invades a red blood cell, the infected cell exports parasite proteins to its surface that act as molecular anchors, binding the infected cell to the walls of small blood vessels and to uninfected cells. The binding is antigen-dependent. The parasite's surface proteins bind more effectively to A and B sugar antigens than to the bare H antigen on type O cells. Type O carriers have measurably lower severe malaria rates because the parasite's anchoring system finds fewer binding targets on the bare surface. Rowe and colleagues measured this in the Proceedings of the National Academy of Sciences, confirming that Plasmodium falciparum infected cells form smaller rosettes with type O cells than with A or B cells. Rosetting is the process by which an infected cell recruits uninfected cells to cluster around it, forming a protective shield that hides the infected cell from the immune system and from splenic clearance. Larger rosettes mean better immune evasion and more severe disease. Type O cells form smaller rosettes because the bare H antigen provides fewer binding sites for the parasite-exported adhesion proteins. Smaller rosettes mean less immune evasion, faster splenic clearance of infected cells, and measurably less severe malaria. The binding reduction translates directly to clinical outcomes because rosetting severity correlates with disease severity across every population studied. Global distribution of blood types is the malaria map. Type O frequency is highest in sub-Saharan Africa and South America, the regions with the longest continuous malaria pressure. In parts of sub-Saharan Africa, type O frequency exceeds 60%, reflecting intense selection pressure across hundreds of generations. Type O frequency is lowest in Central Asia and Northern Europe, regions with minimal historical malaria. The blood type map of the modern world is the fossil record of parasitic selection pressure across tens of thousands of years. The bare surface survived because the bare surface made the parasite's job harder in the regions where the parasite killed the most people. Deletion protects against malaria. The bare surface is the oldest. The evolutionary advantage is clear. But evolution trades. Protection against one threat is purchased at vulnerability to others. The bare surface that hides from the malaria parasite exposes something else. What does the bare surface cost? 3 disease consequences pulling in different directions from one deletion. Cardiovascular advantage. Type O carriers have 5 to 20% lower risk of venous thromboembolism, blood clots forming in veins. The mechanism runs through von Willebrand factor and factor VIII, clotting proteins that circulate at lower concentrations in type O individuals. The A and B antigens on endothelial cells, the cells lining blood vessel walls, protect von Willebrand factor from clearance by the body's protein recycling systems. Type O endothelium, lacking these antigens, allows faster clearance. Lower von Willebrand factor means lower factor VIII, means reduced clotting tendency. The bare surface makes the blood thinner through faster clearance of the proteins that initiate clot formation. The mechanism traces through von Willebrand factor, a glycoprotein that initiates clot formation by recruiting platelets to damaged vessel walls. Franchini and colleagues documented this association in thrombosis and hemostasis. The practical significance: if you are type O and your physician has discussed clotting risk, the 5 to 20% reduction the bare surface provides is a measurable baseline advantage that modifies your cardiovascular risk profile independently of lifestyle factors. The advantage is genetic, permanent, and has been operating since the first type O cell entered circulation. Gastric vulnerability. Type O carriers have higher rates of peptic ulcer disease. Helicobacter pylori, the bacterium that causes most stomach ulcers, binds to surface structures on gastric epithelial cells. The H antigen and related Lewis antigens on the stomach lining may provide binding targets that A and B modifications partially shield. The bare O surface exposes these targets. The epidemiological association, replicated across dozens of studies and multiple populations, is stronger than the mechanistic evidence, which means the increased ulcer risk is measured and real, but the molecular binding specificity is still being characterized. Cholera vulnerability. Vibrio cholerae toxin binds more effectively to O and H antigen structures on intestinal epithelium. Type O carriers experience more severe cholera. The geographic overlap compounds the evolutionary trade-off in a way that illustrates evolution's indifference to individual outcomes. Equatorial populations with the highest O frequency, selected by malaria pressure, carry the highest cholera vulnerability simultaneously. Cooling established this association in clinical microbiology reviews. 1 deletion, 1 bare surface. 3 disease consequences. The malaria protection and the cardiovascular advantage argue for the deletion. The gastric and cholera vulnerabilities argue against it. Every blood type is a trade-off. Surface chemistry optimized under specific pathogenic pressures, producing advantages and costs simultaneously. The 37% frequency represents the equilibrium the competing pressures settled on across thousands of generations. If malaria were the only selection pressure, O would approach 100% in malaria endemic regions. If cholera were the only pressure, O would approach 0. The 37% is the frequency where the malaria advantage and the cholera disadvantage, combined with all other selection pressures acting on an identical surface, reach a balance. The number is not random. The number is the mathematical output of competing selection forces acting on one molecular surface across deep evolutionary time. My understanding of the letter on the card changed the week the trade-off reached specific numbers. 5 to 20% lower clotting risk from the bare endothelium. Higher ulcer risk from the exposed H antigen. Malaria protection from the absent binding targets. 1 deletion producing 3 consequences that pull in different directions simultaneously, each one traceable to the bare surface, the broken enzyme left behind. The card in the wallet is a genetic fingerprint. The fingerprint describes a surface. The surface determines the trade-off. The trade-off has been running since before the first blood type card was ever printed. The letter was never just a transfusion category. The letter was a molecular history. The letter was a molecular trade-off the body has been living with for longer than any written record. How does the fluid carrying these bare cells behave? And then, cells carrying that bare surface circulate through the body as a fluid, with physical properties that change depending on how fast the blood is flowing. Blood is a non-Newtonian fluid. Its viscosity changes with shear rate, the speed at which adjacent layers of fluid slide past each other. In fast-flowing arteries where shear rate is high, red blood cells align in streamlines and the viscosity drops, the blood flowing more easily at higher speeds. The behavior is the opposite of what intuition predicts. Faster flow produces thinner fluid. A Newtonian fluid like water maintains constant viscosity regardless of flow rate. Blood changes its mechanical behavior dynamically as a function of the shear environment it encounters, adapting its physical properties in real time as it moves from arteries to capillaries to veins. In slow-flowing veins and capillaries where shear rate is low, cells aggregate into rouleaux, coin stack formations held together by fibrinogen bridges between adjacent cell membranes, and the viscosity increases. The rouleau formation is reversible as the blood accelerates through a narrowing vessel. The increased shear breaks the stacks apart, and the cells resume individual flow. The transition happens continuously as blood moves between high shear and low shear regions of the circulation, the cells assembling and disassembling their formations thousands of times per circuit through the body. The shear thinning property is what allows blood to flow efficiently through vessels ranging from the 2.5 centimeter aorta to capillaries narrower than the cells themselves. adapting its viscosity continuously to the local flow conditions each vessel segment demands. Blood adapts its physical properties to the vessel it occupies, thin where speed matters, thick where exchange matters. The hematocrit, the percentage of blood volume occupied by red blood cells, sets the baseline viscosity at approximately 42 to 50% in males and 36 to 44 in females. Each red blood cell is a biconcave disc approximately 7 to 8 micrometers in diameter, a shape that maximizes the surface area to volume ratio for gas exchange and allows deformation through capillaries narrower than the cell diameter. 3 to 4 micrometer gaps the 7 to 8 micrometer cell squeezes through by flexing its membrane. Membrane flexibility declines with cell age. The spectrin cytoskeleton beneath the membrane accumulates oxidative damage over the cell's 120-day lifespan, stiffening progressively until the cell can no longer deform through the smallest passages. The spleen tests this continuously. Spleen is a mechanical quality control system. Splenic red pulp sinusoidal passages are slits approximately 1 to 2 micrometers wide. Young flexible cells deform and pass through. Old cells whose membranes have stiffened from 120 days of oxidative damage cannot squeeze through the slits. The spleen traps them. Macrophages engulf and digest the trapped cells. The iron is extracted and recycled back to the marrow for incorporation into new hemoglobin. The heme ring is converted to bilirubin, processed by the liver, and excreted through the bile. The protein components are broken down into amino acids and reused. Every component of the old cell is salvaged. The recycling is complete, nothing is wasted, and the materials from every destroyed cell are rebuilt into new cells carrying the same bare surface the gene guarantees. The bone marrow produces approximately 2 million new red blood cells per second to replace the 2 million the spleen destroys per second. Complete population turnover every 4 months. The blood you carry today is entirely different cells from the blood you carried in March. Every type O cell produced by the marrow carries the bare H antigen. The broken enzyme guarantees every cell expressing one deletion through identical surface chemistry for 120 days each before the spleen removes it and the marrow replaces it. The mutation is permanent. The cells are temporary. The surface condition persists because the gene persists. Every 4 months, the entire population of red blood cells is replaced, and every replacement cell carries the bare surface, because the marrow reads the same corrupted gene instruction for every cell it produces. The turnover is invisible. You carry this blood type at 70 that you carried at 7 through dozens of complete population replacements, because the gene that determines the surface never changes. Hemoglobin inside each cell delivers oxygen through a mechanism that targets delivery to the tissues that need it most. 4 oxygen-binding sites per hemoglobin molecule. The first oxygen molecule that binds changes the protein's conformation, making the second binding site more receptive. The second binding makes the third easier. The third makes the fourth nearly automatic. Cooperative binding, each binding event facilitates the next. The loading curve is sigmoidal, near complete saturation in the lungs within the first pass through the pulmonary capillaries. The cooperativity solves an engineering problem. Without it, hemoglobin would need much higher oxygen partial pressures to reach full saturation, requiring longer transit time in the lungs and reducing the body's maximum oxygen delivery rate. The cooperative mechanism allows near-instant loading, maximizing the oxygen each red blood cell carries into the arterial circulation. Each hemoglobin molecule carries 4 oxygen molecules when fully loaded. Each red blood cell contains approximately 270 million hemoglobin molecules. Each fully loaded cell carries over 1 billion oxygen molecules into the arterial circulation. Bohr effect determines where the oxygen is released. Tissues with the highest metabolic demand produce the most carbon dioxide and the most hydrogen ions. The carbon dioxide and hydrogen ions shift the hemoglobin binding curve rightward, reducing hemoglobin's grip on its oxygen at exactly the sites producing the most metabolic waste. The muscle working hardest receives the most oxygen because the hemoglobin arriving there releases the most. Targeted delivery by destination chemistry. The tissue determines the delivery through the waste products it produces. Carbon monoxide occupies the same binding site as oxygen with 200 times greater affinity. One carbon monoxide molecule on one of the 4 sites shifts the remaining 3 sites to grip their oxygen more tightly, refusing to release it at the tissues. The hemoglobin carries oxygen but will not deliver it. You do not die from a lack of oxygen in the blood. The blood carries plenty of oxygen. You die from hemoglobin that holds the oxygen it is carrying and refuses to release it at the tissues. The pulse oximeter reads normal saturation because the hemoglobin is fully loaded. The tissues are hypoxic because the hemoglobin will not unload. The measurement lies. The delivery fails. Treatment requires 100% oxygen, or hyperbaric therapy, to competitively displace the carbon monoxide from the binding sites through mass action, flooding the hemoglobin with enough oxygen to overcome the 200-fold affinity disadvantage through sheer concentration. The carbon monoxide headache, the confusion, the loss of consciousness all arrive while the blood appears fully oxygenated. The silent lethality of carbon monoxide poisoning traces entirely to hemoglobin doing its cooperative binding job too well. The molecule evolved to grip oxygen efficiently, and carbon monoxide exploits that efficiency by fitting the binding site with even greater precision than the molecule the site was designed for. Whether your type O status, your clotting profile, your gastric health, or your cardiovascular risk should inform specific clinical decisions is a conversation with your physician. The physics teaches what the bare surface does to each system. The clinician evaluates what your specific risk profile requires. The letter on the card represents a molecular surface you have carried on every red blood cell in the circulation without knowing what it physically means. One nucleotide deleted from position 261 on chromosome 9. One enzyme that misfolds and cannot function. One surface left bare where every other blood type carries sugar chains the immune system can recognize and destroy. The bare surface gave the universal donor advantage, the malaria resistance, and the cardiovascular benefit. The bare surface gave the gastric vulnerability and the cholera susceptibility. One deletion, one broken enzyme, 25 trillion bare cells. The number is calculable. Approximately 5 million red blood cells per microliter of blood, approximately 5 liters of blood in circulation, producing every cell in the circulation, each carrying the bare H antigen. The broken enzyme guarantees. Every advantage and every vulnerability traces to a single missing nucleotide that broke one enzyme on one chromosome, and the surface chemistry it left behind has been shaping the body that carries it for longer than any civilization has existed. The letter on the card in your wallet was a molecular autobiography written on every cell in the circulation, carried silently for a lifetime.